Welcome friends and welcome to my series of video lectures on design of RCC structures. We are in chapter 5, shear design of beams. This video lecture is RCC 5.2 IS specifications for shear design of beams. The expected learning outcomes from this video lecture are 1. To check nominal shear stress for maximum shear stress. Second, to state IS specifications regarding shear reinforcement. The contents of this video lecture are 1. Review of shear behavior of beams. Second, critical section for shear. Third, check for maximum shear stress. Fourth, shear resistance of beams. Fifth, reinforcement detailing and zones of shear stirrups. We are going to use some key terms in this lecture. Shear design, critical section for shear, nominal shear stress, maximum shear stress, shear resistance of beam, bent up bars, shear stirrups, minimum stirrups zone. Friends, we have our best friend Smarty with his tips. Write down your own notes while watching this video. Pause or rewind the video whenever required. Do solve the formative and summative assessment quizzes given in the video. Friends, in the earlier video, we have already studied in detail the shear design of beams. In this slide, we will have a brief and quick review of the process of shear design of beams. The first point is that in beams, shear forces arise due to variation in bending moment along the span. As seen in this diagram, there is a constant variation of bending moment, and that is giving rise to the existence of shear force. We know that it is impossible to have a beam without a uniformly distributed load. If we have got a uniformly distributed load, we are bound to have variation in the bending moment along the span of the beam. Because the beam is having at least its own self weight, which is in the form of uniformly distributed load, it is not possible to get rid of the self weight. So it is not possible to have a beam without at least one uniformly distributed load. This brings us to the fact that it is impossible to have beam with pure bending. That means we must be having every time some variation in bending, and that is why we will always have some shear force at every cross section. This makes it necessary to consider the behavior of beam in shear in greater detail. Now we have seen in the last video that there is shear cracking, and we can divide the beam in three zones 1, 2 and 3, and the shear cracking takes place differently in the three different zones. We know that the shear is critical or maximum near the supports. So zone 3 is critical for shear, just as zone 1 is critical for flexion. So we have seen that at the support or near the support, we can get elements in pure shear as shown like this. Element in pure shear means element having no bending stresses, only shear stresses. So this is an example of element in pure shear, and here the result of pure shear is that one diagonal is stretched. That means we get tension along one diagonal of the element, as we get diagonal compression along the second diagonal. That is why the result of maximum shear or critical shear in the beam, which is usually at the supports, the result of this is that we get diagonal tension and diagonal compression in the member. So here we see a picture or a real beam in which we see 45 degrees inclined cracks arising from the support. So this was another point of review. Now we come to the fact as how to design a beam. So what is the meaning of design of a beam for shear? So here we make it explicit. Design of beam for shear. Shear design of beam involves making provision for shear resistance such that the shear resistance of beam is more than the actual shear force called design shear force VUD developed at the critical section of the beam. So what we are supposed to do is we are supposed to decide the critical section, the section at which the shear force is critical, and at that critical section we calculate the value of shear force that is called as design shear force VUD. So this VUD is calculated as at the critical section, and in the process of design we are supposed to provide the measures so that we develop a resistance in the beam which is equal to VUR. This VUR should be such that it is greater than VUD. So if the resistance is greater than the actual shear force, we can say that the beam is safe in shear. So design of shear for beam is nothing but a handshake between the shear resistance VUR obtained from the design and with the actual design shear force which is developed due to the loads. Now the shear resistance of the beam will be derived from two factors or two sources. One is shear resisted by concrete and second is shear resisted by steel. The greater detail of this fact will be studied further in this video. Just as we saw in the previous slide, that to design a beam for shear means to develop shear resistance in the beam VUR which is greater than the shear developed at the critical section, that is the design shear force. So first of all we have to know how much shear force is to be resisted. So that value of shear force, as we said, is the design shear force, that is VUD. Now what is VUD? VUD is the shear force at the critical section. Here comes the concept of critical section. We know that in general shear force is maximum at the supports of the beam. So when it is maximum at the supports of the beam, actually we should take the support shear as directly as the critical section shear. But IS 456-2000 is giving us some allowances regarding deciding the shear design shear force. So the critical section may not be always this direct support section. So let us study in detail what the IS is saying about the critical section. Critical section for shear means the section in the beam at which the value of shear force is taken for design. That means you will have to calculate the force VUD at a section which is called as critical section. Now IS code further says when the reaction in the direction of applied shear introduces compression into the end region of the member, sections located at a distance less than D from the face of the support may be designed for the same shear as computed at distance D. I can understand that this sentence is quite long and the language of IS code is just language like a book of law, but we will understand this sentence with the diagrams quickly. The above clauses are applicable for beams generally carrying uniformly distributed load or where the principal load is located farther than 2D from the face of support. In the cases other than the above, critical section shall be at the face of support. So three facts have been narrated in these three statements. We will understand all the three facts by actual examples. Let us consider the situation here. This is a simply supported beam carrying UDL and having column under the beam. Usually the columns will be under the beam. Rarely they may be above the beam, but normally the columns will be under the beam. Now in such a situation, actually the column is offering a reaction to the beam in upward direction. So this green arrow indicates the reaction of column on the beam, whereas the load is pushing the beam downwards. So in this region, in the support region of the beam, we get compression induced only in this region. So this compression is induced. So in the first sentence, as they have said, that in the direction of applied shear introduces compression into the end region. If that is the situation, so here the reaction, this reaction is inducing compression in this zone near the end. If that is the situation, which is the situation when the column is acting, column is below the beam, then the IS code is saying the shear VUD may be calculated at a distance D from the face of the column. So this red line is the critical section, which is located at a distance small d. What is small d? It is the effective depth of the beam. So when the situation is like this, which is a very common situation, that you are having a UDL and you are having a simply supported beam and the column is lying below the beam, we can say that the critical section for shear can be taken at a distance d from the face of the column. Obviously, this value of VUD, that means the critical section here, this value will be less than the value calculated here at the face of the support. It will be less because of the reduction of this load. So this advantage IS code is giving us that you can take a lower value of VUD for calculation purpose because compression is induced by the column reaction and the load at this section. So this is situation number 1, in which the critical section is taken at a distance small d from the face of column. Second, if that is the situation, obviously you will get VUD, that is the design shear force, equal to WL by 2 minus WU into D. So this minus WU into D reduces this value of WL by 2 by some amount, and this amounts to economical design. So if you want an economical design, IS code is giving us this provision that don't take the critical section at the support, take it away from the support at a distance D. So that is the first situation. Now the second situation is like this. As we said right now, here you will see the same thing, but the column, this column has gone above the beam. This means that the beam is at the bottom of the column. That means that the beam is suspended from above. So you are having a column above the beam. So this means that you are not having the compressive reaction of the support now. Again, we can see the directions. Here the column is pulling the beam up. The reaction of column is that of pulling the column, pulling the beam up, whereas the load is pushing it down. So in this region, we don't get compression, as in this case, we get tension. So if that is the situation, that means if the column is not offering compressive reaction on the beam, it is offering a tensile reaction on the beam. In that case, IS code is saying, in all other cases than the above, critical section shall be at the face of support. Here you see the face of support, face of column. This is the face of column. So we have taken this red section VUD. The shear force is not at a distance D, but it is exactly along the face of the column. So this is the second situation. So when we will be solving numerical problems, we have to think about what type of beam are we having. Are we having a suspended beam like this, or are we having a beam like this? If we are having a beam like this, we will calculate VUD by this formula, so that we get the advantage of reduction by this WUD, so that our design becomes economical. In the second situation, as we said, this critical section shall be at the face of column. In other cases, means cases like this, right? So VUD is WL by 2, not minus WUD. So this was the second situation. The code is talking about the third situation also. That third situation is this. The above clauses are applicable for beams generally carrying uniformly distributed load. That means these. But they are also talking, IS code is also taking cognizance of a beam where there is no UDL. Look at this beam. This beam is not having UDL. There is a point load P1. UDL is absent. So IS code is saying if you are having a point load, say P1, and that load is acting at a distance, you can see here it is acting within this D. Okay, it is acting within effective depth of the beam, right? So then in that case, IS code is saying you cannot take the critical section at a distance D. You have to take the critical section at the face of the column. You have to take it at the face of the column. What the IS code is saying? Where principal load is located farther than 2D from the face of the support. Farther than 2D from the face of support. So from the face of support, if the point load is away by more than distance 2D, more than twice depth distance from the face of column, then only you can take this critical section at effective depth D, but otherwise you have to take it at the face of the column itself. This situation is not a very common situation, but IS code has given a provision, that's why we are studying it. Now look here. Here we find that here also we are having a point load P2, and at what distance is this point load? You can see here it is at a distance greater than 2D. Look here, this P2 is at a distance greater than twice D from the face of column. Okay, that means it is farther than 2D from the face of the support. Okay, if that is the situation, this above statement applies. What is that above statement? It says that you take the critical section at a distance D. So you can see the critical section VUD you are calculating at this red line, which is at a distance D. Here that red line was at the face, but now it is at a distance D from the face of the column. So this is the fourth situation in which we are getting a point load which is acting at a distance greater than twice D from the face of column. In that situation, you have to take, or you can take, the critical section at a distance small d from the face of the support or face of the column. So these are the four possibilities according to this statement of IS code regarding the critical section for shear. So for the calculation purpose, we are going to use all these clauses in the situation when we will be solving the numerical problems. Friends, in this slide we are going to discuss about diagonal compression and check for tau C max. This is one more IS specification that we are going to study. In this video lecture, as we have said in the title of the lecture itself, that we are studying various IS specifications regarding shear design of beams. So the first specification we saw about critical section, location of critical section. Now the second specification is about what we call a check for tau C max. We know that this is the element in pure shear and this is the critical element we are talking about. So we have got diagonal tension and diagonal compression. Now the question is how to resist this diagonal compression and diagonal tension. For that, the diagonal compression will be resisted by concrete alone. We know that concrete is capable of taking compression. So the diagonal compression, these blue inward arrows, they will be resisted by concrete alone. But the IS code is putting a condition on tau C max. We will see what is this tau C max. And the second thing is the diagonal tension. Diagonal tension will be resisted by shear reinforcement, which we will see in the next slide. In this slide we will see how this diagonal compression is resisted by concrete and what is this check for tau C max. So this is the second important specification by IS code, clause 40.1 page 72 and table 20 page 73 of IS 456-2000. Check for tau C max. Let us understand what is this check about. To take care of diagonal compression, we have to take the check that tau V is less than tau C max. Otherwise, we have to revise the design. What is this check? Just look here. When we get a problem, when we get the critical section, as we discussed in the earlier slide, we calculate the value of VUD. That means we calculate the shear force at the critical section by using our usual methods of structural mechanics. After we calculate that VUD at the critical section, we have to calculate VUD upon BD. That is the value we call as tau V. Tau stands for shear stress. Remember, tau, the symbol tau stands for shear stress. So we call that as nominal shear stress. So we have to calculate the nominal shear stress, which is that VUD upon BD. VUD upon BD, that is called as nominal shear stress. Exact distribution of shear stress across the concrete section cannot be determined. It is theoretically or even practically impossible to determine the shear stress distribution diagram for concrete section. It may be convenient and easier for steel sections and other sections. It's not, because of the behavior of concrete itself is little understood. It is difficult. So a simplified concept of nominal shear stress is introduced by IS 456. From our side, it is to be simply remembered that after we have calculated VUD, the design shear force, we have to calculate the nominal shear stress tau V equal to VUD upon BD. BD is the breadth of the beam and depth of the beam, effective depth of the beam, where VUD is ultimate design shear force at critical section, as we discussed in the earlier slide. So we calculate this tau V. After we calculate this tau V, this is left side of this equation. We have to check whether that tau V as calculated is less than tau C max or not. So we have to calculate this second value, tau C max, and we have to compare both the values and check whether tau V means actual shear stress developed at the section. In the earlier slide we talked about design shear force, VUD. Now this is shear stress, which is VUD upon BD. So this is tau V, which should be less than tau C max. What is tau C max? Tau C max is the value maximum shear stress, and it is to be taken from table 20 of the IS code. So for getting this value of tau C max, tau stands for shear stress, C stands for concrete, and max for the maximum limit of this value. So here we are reproducing table 20 of the code. It is maximum shear stress tau C max in Newton per mm square. If you look at this table, it's a very simple table. You are having grades of concrete M15, 20, 25, 30, 35, 40 and above, and you are getting the values of tau C max. So simply look at the grade of concrete that you are using in your problem. Suppose you are using M25 grade concrete. So if it is M25, you have to use this tau C max as 3.1 Newton per mm square. So 3.1 Newton per mm, just put that value here and compare that value with this tau V value. Tau V and tau C max. So whatever value you get about tau V, if it is less than this tau C max, then you can say that tau V is less than tau C max. In that case, you can say that your design is safe about diagonal compression. Okay. Why diagonal compression is also critical? Because if the beam fails in diagonal compression, that failure is sudden. That is the greatest disadvantage. It is a sudden failure because it is brittle failure of concrete, and that is why IS code has put this condition that your maximum shear stress tau V should not be greater than this value 3.1 for M25 and so on. So this is the first check we have to take. So after we have calculated VUD, we have to calculate tau V and we have to check whether it is greater than tau C max, less than tau C max or not, and that is how we are taking care of this diagonal compression. Now in the next slide we will see how we will be taking care of this diagonal tension. What are the various IS specifications? So this was all about the check for tau C max according to IS 456. So friends, in the previous slide we have seen how to calculate VUD, that is the design shear force at the critical section. As we have seen, the design for shear is nothing but a game between VUD versus VUR. Now in this slide we will understand the various ways in which we can develop shear resistance in a beam. So shear resistance of beam, we are calling it by the symbol VUR. This is analogous to MUR, that is moment of resistance in case of the flexural design of beam. So we are continuing the similar fashion. Now let us come to the sources of shear resistance of beam. The shear resistance of beam can be derived from the two materials, that is concrete and steel. So we are calling this VUR as the shear resistance of beam. It consists of concrete, and concrete resists a shear force of VUC. Similarly, the shear reinforcement is consisting of two parts, shear stirrups and bent up bars. Shear stirrups and bent up bars are the two ways in which the steel will resist shear. So stirrups will resist VUS and bent up bars will resist VUB, so that we have got VUR, that is the shear resistance, equal to VUC, the resistance of concrete, VUS, the resistance of shear stirrups, and VUB, the resistance raised by the bent up bars. Here we see a typical reinforcement detailing of a beam which is designed for shear. Here we see that the vertical stirrups are provided. So vertical stirrups are provided in the form of these rings, shear rings or the steel rings, and they will resist the shear force of VUS. Now we will see this bent up bar also. This is a bent up bar. Let us understand the concept of bent up bar in a little greater detail. So we know that at the center of the beam, at the midspan of the beam, we design it for bending moment as the flexural design in case of a simply supported beam subjected to uniformly distributed load. So the midspan section, for example, is, let us say, having 3 bars of the flexural steel. So we have got 3 bars, and we will find that as we go from the central or midspan section to the support section, the bending moment goes on decreasing. We know that bending moment diagram is parabolic and the bending moment is 0 at the support. It is maximum at the midspan. So we design the beam for bending moment at the midspan section, and the steel required at that section is this, say for example 3 bars. As we will go from the center to the support, the bending moment will reduce and the same amount of steel, that is 3 bars, will not be required as we go towards the supports. That is why there will be a particular section at which only 2 bars may be sufficient and 1 bar may become redundant, you can say, not essential. In such a situation, from such a section, we can bend that extra bar up and continue at top at the support. So this becomes a bent up bar. So it is important that you have to bend the bar at such a section such that it is no more required for resisting bending or for resisting the flexural tensile stresses. So we can make use of this bottom bar at proper location to resist shear also. So this is what we call as the bent up bar. Now we will start understanding the contribution of each material step by step. Let us consider the shear resisted by concrete. How much shear concrete will resist? So shear resisted by concrete is given by VUC. Now according to IS 456-2000, we can calculate the value of shear resisted by concrete VUC by the simple formula VUC equal to tau C BD. B and D are the dimensions of the section. Now in this tau C is called as design shear strength of concrete, and the value of this tau C is required to be taken from a table which is table 19 given in IS 456-2000. To find out this value from table 19, we require one quantity called AS, which is bottom steel continued at support. Let us have a look at the table 19 of the IS 4. This is table 19 directly taken from IS 456-2000, design shear strength of concrete tau C Newton per mm square. If we look at the table, we'll find that the first column is having the heading 100 AS upon BD. So depending upon the values of 100 AS upon BD, we are getting all these values of tau C. Now on the right side you will see that the values of tau C are given for various grades of concrete. For M15, 20, 25, 30, 35 and 40, we are getting different values of tau C, and all these values for a given grade of concrete are again depending upon the factor 100 AS upon BD. Here AS is as shown here. AS is bottom steel at the support and BD is the cross sectional dimension. So we have to calculate how much steel is continued at the bottom. Now this continued bottom steel at support has a significance. We can see here two sections. At the midspan section we have got AST, as we call in flexural design, AST 3 bars, and at the face of column, look here, at the face of column, since one bar is bent already up, we will have only 2 bars continued. So at the face of column we will have 2 bars, whereas at the midspan we will have 3 bars. Now while taking the value AS, you have to take the number of bars or bottom steel available at the support. So at this support we will say that only 2 bars are available. The third bar has been taken already up at an earlier section. So like this care is to be taken while calculating this factor of 100 AS upon BD. Now then using the table and getting the value of tau C is as usual. Here for example, if you have got 0.25 as the value of 100 AS upon BD and you have got concrete grade M25, your value will be 0.36 Newtons per mm square. That will be the value of tau C. And you put the tau C here and you multiply by B and D, you get the shear force resisted by concrete. Now there is one small complication involved, that the values of 100 AS upon BD are 0.15, 0.25, 0.50 and so on. The table is continued here also. Now whatever value you get for this 100 AS upon BD, that value may not be exactly 0.25 or exactly 5.50. It may be between the two values. Now in such a situation, whenever we are using any table, we are used to using a method what we call as the method of linear interpolation. So the intermediate values can be interpolated linearly. So let us take a very small example of linear interpolation also here. So let us take example of linear interpolation for using this table, and let us consider a value PSB. This PSB is nothing but 100 AS upon BD. So this 100 AS upon BD, in short we are calling it as PSB. Let us assume that we have calculated this value and it is 0.47%. Now this is 0.47%, that means 100 AS upon BD This value is 0.47%. Here we are getting 0.25 and 0.5. So in between these two values, I am calling this 0.25 as A and B as 0.5. And between A and B, I am getting this value 0.47. So this I am calling as E, right? Now let us assume that we are using concrete grade M20. We are using concrete grade M20. So for 0.25 the value was 0.36. Corresponding to 0.50 the value of tau C was 0.48. So our value corresponding to this 0.47 is going to be between 0.36 and 0.48. So let us call that value as F. So you can see A, B are the two values, extreme values. C and D are other two extreme values of tau C. In between we want E, we want to interpolate the value for F for the corresponding value of E. So F is equal to how much? That is the question. Now for the value of F, we have got this linear interpolation formula. Here A, B, C, D, E, these symbols are used, and F is equal to, you just put the values of all these A, B, C, D, E and you will get the answer. What is A, what is B, that is shown here. You can take a screenshot of this particular part of this video and you can calmly do the calculations with yourself and confirm. So if you put A, B, C, D, E values in this formula, you will finally get this answer of F as 0.466. 0.466. You can confirm that this answer lies between 0.36 and 0.48, obviously 0.466. So that is how you can calculate the value of tau C, and you can put it here and you can finally get the value of shear resisted by concrete. Now we proceed for the calculation of shear resisted by the stirrups and the bent up bars. Now before we proceed for the bent up bars, we will first of all consider the concept of minimum shear stirrups. The shear stirrups are provided here. The shear stirrups will look like this. The shear stirrups, these rings, these vertical rings, these rings are called stirrups, shear stirrups. They are made up of a single bar which starts like this. It bends like this, bends here again, it bends at 4 locations and bends back like this. And these straight line portions are of 6 phi, 6 into phi. Phi is diameter of the stirrup bar, and this angle is also supposed to be 135 degrees. So these are some specifications related to the dimensioning of the and the anatomy of what we call as the stirrup ring. Now we can say here that this is called a two-legged, one ring closed stirrup. What is the meaning? Two-legged. So this vertical portion of the stirrup is called as leg of the stirrup. So this is leg 1, this is leg 2. So two-legged, one ring. This is a single ring and closed stirrup. So this is what we call as a single ring, two-legged closed stirrup. This is the same which we have provided here. Okay. Now the same stirrup ring is looking at simple lines in this section. Now this is the most common form of stirrups that we get. So other two forms are not of much use, but for just academic purpose we will just know their names and their anatomy. So this is the first type, common type. Then this is second type. This is also having two legs, two-legged, one ring. This is also having only one ring, but this is not closed stirrup as this. It is open. You can see that here the bar is not existing. This part of bar is not existing. So this is what we call as a two-legged, one ring open stirrup. In the open stirrup, this length is required to be little more than this. This was 6 phi. This is 8 phi. This is the second type of stirrup. This is the third type of stirrup in which you will see two rings put one against the other, right? So this results in a four-legged stirrup. You get four legs, 1, 2, 3, 4. These vertical four legs are there, and this becomes a four-legged two-ring closed stirrup. So this was one more example. Some more examples of stirrups can also be found. We can sometimes get inclined stirrups also. IS code provides for inclined stirrups also, but they are very rarely used, so we are not right now considering them. So these are the common forms of shear stirrups. Now if you look at this diagram back, you will find that the spacing of the stirrups is shown here. The spacing of shear stirrups. The spacing of shear stirrups according to IS code is calculated by this formula. Suppose you want to resist a shear force of VUS, some value VUS, then you will have to provide some spacing of those stirrups. So that spacing will be calculated by this formula. This formula is 0.87 FY ASV upon VUS, that is the shear force you want to resist by the stirrups. Now here Fy stands for the yield strength or the characteristic yield strength of the material of the bar of the stirrup. It has nothing to do with these bars. These bottom steel bars, they may be having different grade of steel, and the stirrups may be having different grade of steel. So we are right now talking about stirrups. So this Fy stands for the grade of the bar for stirrup. Now this ASV is number of legs of the stirrup into area of one leg of the stirrup. This is where this legged terminology comes into play. So if you have got this stirrup, for example, a single stirrup is having two legs, then ASV, area of steel in shear. So one leg, one stirrup will have two legs in this case, and that is why we will have number of legs as 2 and area of one leg. For example, if this is an 8 mm diameter bar for the stirrup, so this will have 50 mm square area. This also leg will have 50 mm square area for 8 mm bar, and this will together give us 50 plus 50, 100 mm square. So ASV will be 100 mm square if you are using a 2-leg stirrup. If you are using a 4-leg stirrup, this will be 50 into 4, that will be 200 mm square, like that. Now using this formula we can calculate the spacing of the stirrups, but that spacing is not the final value of spacing. IS code is putting some conditions over that value of spacing also. If that spacing exceeds the value 0.75 into effective depth small d, or it exceeds 300 mm, these are two independent values. So you have to compare this value of SV that you can get from this calculation, and you have to check whether it is exceeding this value or this value or not, which means finally that we have to take the lowest of these three values. SV, whatever SV value you will get, then you have to check it with this 0.75D, you have to check it with 300 mm also, and whichever is the least value of the three, we will be taking as the stirrups. So that is the spacing of stirrups. So here we have understood how to calculate the spacing of the stirrups to resist a given value of ultimate shear force. Now we come to this concept of minimum shear stirrups. Now as we have seen, this design for shear is just a game between VUD versus VUR. We are collecting shear resistance from the materials of the beam. Concrete has contributed by VUC. Okay. Now if you find that VUC, entire VUC is this taken is sufficient for this VUD, right? It is possible that your VUD is say 100 kilonewton and your VUC is 120 kilonewton, for example. So VUD and VUC. This VUC itself may be enough to resist all the shear that you want to resist. So the game is over. Okay. In that case, what will happen? The question of these stirrups will not come at all. That means this entire area, this entire source will not be required to be used. But IS code does not allow that. IS code says that even if you come across a situation where the concrete is alone enough, that means VUC is alone sufficient to resist this entire VUD, you are not allowed to say that we will not provide any stirrups at all. So IS code is saying that no beam in any condition will be without shear stirrups. You must provide some minimum shear stirrups. Minimum shear stirrups. So what are the requirements and conditions for that? IS code is why it is insisting on this. Once the shear is actually resisted, why IS code wants that we must provide some minimum quantity of stirrups. IS is telling why should you provide a minimum stirrups, and IS is also telling how much spacing should you provide for that. So there are 4 reasons for providing minimum shear stirrups. The first reason is to prevent sudden failure. What the stirrups are doing, they are not only providing the shear resistance, but they are providing ductility to the concrete also. You know that concrete is brittle, and every time this concrete failure is a sudden failure, catastrophic failure, and that is why the advantage of the minimum shear stirrups is that the minimum stirrups will prevent sudden failure by offering some ductility. Second is to prevent premature failure in case of loss of bond. If there is a situation where the bond between concrete and steel is lost, then the minimum stirrups will prevent premature failure. Third reason is to provide tie to hold main bars. Remember that there are 3 bars at the bottom. These are the flexural steel bars. At the top we are having 2 anchor bars. 2 anchor bars are provided. Now to hold these 3 bars and these 2 bars in proper position, these shear stirrups will be used as a tie. So they will work as tie to hold the main bars and the anchor bars of the beam. The fourth reason for providing minimum shear stirrups is to confine the concrete. Since when you get the entire skeleton of the shear stirrups and the bars, they confine concrete, and that is advantageous to resist shear. So these are the 4 reasons why IS code is insisting on minimum, at least minimum shear stirrups. Now IS code in its clause 26.5.1.6 on page 48, it tells us also how much minimum shear stirrup should you provide. That minimum is defined, and this is the formula given by IS code: ASV upon BSV, not greater than or should be greater than or equal to 0.4 upon 0.87 F1. If we combine this, here also SV is involved. This SV stands for minimum, the spacing for minimum shear stirrup, and here this SV stands for the desired shear force is to be resisted by these stirrups. So if we combine this formula and this formula, we will finally get a convenient formula that VUS minimum will be equal to 0.4 BD. VUS minimum will be 0.4 BD. What is this? This VUS minimum is the shear force resisted by the minimum stirrups. This equation will give us the spacing of the shear stirrup, minimum shear stirrups, and this formula will give us how much shear force that minimum shear stirrups, those minimum shear stirrups have resisted. So this was about the minimum shear stirrups. Now the next source is bent up bars. The next source is bent up bars. What is the provision for bent up bars? We have already seen right now what is the concept of bent up bars and how we are using the bent up bars and where from they are to be used as bent up bars. Now IS code is saying that to calculate the shear resisted by bent up bars, you have to use this formula. Clause 26.5.1.6 page 48 tells us that the VUB, shear resisted, ultimate shear resisted by B, stands for bent up bars. It should be least of or the smallest of 2 values. One is VUD minus VUC upon 2. VUD is this ultimate value of the design shear force, minus VUC, that is the shear resisted by concrete. So half of that, this is one value, and second value is, this is a small formula, 0.87 Fy. Now remember, this Fy is now having the value of the bent up bar. Now we are not talking about the stirrup, we are talking about this bent up bar. So the grade of the steel of this bent up bar, that value of Fy we have to take. N is number of bars bent up, AB is cross sectional area of one bent up bar, and sine alpha is the sine of angle alpha at which the bar is bent. Usually this angle alpha is 45 degrees. So this is the formula. Here N is number of bent up bars. Usually we will bend only one bar, and we are allowed to bend the bars. Number of bars is decided by how many bars you already have. If you have got only 2 bars in the beam at the mid span, then you are not allowed to bend any bar. At least 2 bars must continue at the bottom at the support. So that is usually you find that this first value is smaller than the second value. The second value is much greater, but the first value is smaller, and that is why there is no point in bending more number of bars, because this first value is going to govern this equation. So this finally gives us the value of the shear force resisted by bent up bars. So this was the contribution of bent up bars to resist the shear. Now, with this much of understanding of the shear resistance of beam VUR, we will take a very small numerical example so that the things get clear further. Okay, we know that we are talking about the game between VUD versus VUR. VUD versus VUR. Now let us imagine that in some beam you have to resist VUD as 190 kilonewton. This VUD at critical section, VUD has been calculated as 190 kilonewton. So what you want to do is, you want to develop a shear resistance equal to 190 kilonewton. Now what are the sources you have? You have got concrete, you have got minimum stirrups, and you have got bent up bars. These minimum stirrups will resist 0.4 BD and all these things. So according to these three formulae, you can calculate the shear resistance. So on the right hand side, let us calculate shear resistance. First, VUC. Suppose you do all the calculation, you find that VUC is 70 kilonewton. Okay. Then you do the second calculation. This VUS minimum is compulsory. You want to resist 190 kilonewton. Concrete has resisted 70 kilonewton. So if you compare these two figures, you find that concrete alone is not enough to resist this 190. So you will try the minimum stirrups. You already have to provide minimum stirrups. So they will resist 50 kilonewton, for example. Okay. Let us imagine. So the total shear resistance by these two will be 70 plus 50. Okay. So this will become 120. So together they will resist 120. If they resist 120, again VUD is 190. So these two are not enough. If they are not enough, we will go for the next source. If these two were enough, the design would end here. You would not go for any bent up bars because they are no more required. But in this problem, we find that they are required. So if you go further and find out this VUB also, by calculation you find that VUB is 40 kilonewton. Okay, so you added one more source of resistance. Now what is the total? This is 70 plus 50, 120 plus 40, 160. So this total VUR now, due to these three sources, has become 160 kilonewton. But you find that its VUD is still more, 190. So it clearly means that the three sources are not enough. These three sources are not enough. What is the fourth source? There is no fourth source as such. There are only three sources. In that case, what you have to conclude? You have to conclude that You will provide concrete, that is okay. You will provide bent up bar, that is also okay. But this VUS minimum will not be sufficient. This 50 will not be sufficient. You will have to provide the shear stirrups in more quantity so that they will resist more shear and they will fill up the gap. So 70 plus 40, this is 110 and this is 190. So you will provide stirrups not to resist a shear force of 50, but you will have to provide it. So 140, so you will have to provide 180 kilonewton resistance by providing shear stirrups. So here this VUS will come out to be 80 kilonewton, and that will what we will be called as designed shear stirrups. Okay, so this is the last option left to you. Just remove these minimum stirrups and replace them by closer stirrups or more quantity of shear stirrups. So that is, these are the stirrups, they are also stirrups, these minimum stirrups are also stirrups. Only thing is, designed shear stirrups are having closer spacing or more steel than the minimum shear stirrups. Okay, so these designed stirrups are used when minimum shear stirrups, that means we use as minimum plus bent up bars and plus concrete, they are not enough to resist the shear, not sufficient. That means your VUD, as you can see here, is greater than VUC plus VUS minimum plus VUB. We have taken a numerical example so that these things could be understood better. If this situation is there, we have to design shear stirrups for a closer spacing given by this formula, where this VUS is to be taken as VUS equal to VUD minus VUC minus VUB, and that value, as we said, 80 kilonewton in this case, so that value is to be considered. So this is how the shear resistance is finally developed to meet the requirement of VUD, and the design of beam can be carried out like that. So in this slide we have seen the sources of shear resistance, and we have also indirectly seen how the design procedure of the shear design of beam goes. Friends, before we conclude this lecture, we will have a formative evaluation self-test. We have a question. Prepare a one-page overview of all IS specifications for shear design of beams which we have studied in this lecture. So do solve this exercise, and let us now proceed for the last slide. So let us sum up the lecture. The title of the lecture was IS specifications for shear design of beams. The expected learning outcomes from this video lecture were: 1. To check nominal shear stress for maximum shear stress. Second, to state the IS specifications regarding shear reinforcement. The contents of this video lecture were a review of shear behavior of beams, critical section for shear, check for maximum shear stress, and the fourth, shear resistance of beams. We used some key terms in this lecture: shear design, critical section for shear, nominal shear stress, maximum shear stress, shear resistance of beam, bent up bars, and shear stirrups. If you have understood, it's okay. If you have not understood, contact your teacher for doubts or queries. Also rewind and pause and try to understand. After that, we have got a summative assessment quiz. Attempt the online summative assessment quiz given in the Google quiz form, and the link is given in the description portion under the YouTube video lecture, and do attempt the quiz. Now, our next video lecture, RCC 5.3, is going to be on a numerical problem on shear design of beams. Friends, to conclude, we have got our best friend Smarty here to say thanks. So thanks for watching this video and goodbye till we meet in the next video.